So, the final block. I've talked about greenhouse gas emissions. I've talked about emission reduction in the technical sense, what it would cost to reduce emissions and what policy instruments you would use. That was block one. I've talked about the impacts of climate change. That was block two. So now we're in block three, where I'm going to put them together. Today, I'm going to talk about optimal climate policy, essentially doing a cost-benefit analysis, bringing the costs of greenhouse gas emission reduction together with the costs of climate change. That's the topic for today. And then next week, I'm going to talk about international environmental agreements. So today, I'm going to assume that there's a global social planner, and next week, I'm going to do away with that assumption. Before I do this, I'm first going to talk about international climate policy and the goals that it set. In Rio de Janeiro in 1992, there was the second conference on environment and development. The first one was in Stockholm in '72. In Rio in 1992, a range of treaties was negotiated, including the United Nations Framework Convention on Climate Change. Essentially what the UNFCCC did, this is exactly the wrong one, right? This is right. Essentially what the UNFCCC did was set the rules for international climate negotiations. So it's mostly procedural, but it also had an Article 2 that sets out the ultimate objective of these climate negotiations. The UNFCCC was a resounding success. It was negotiated in 1992. By 1995, basically all countries in the world had signed up to it. There's a few countries holding out, the Vatican, North Korea, but all other countries essentially signed up. Part of that success is due to the fact that it's a procedural convention. It just promises that diplomats get together every year to talk about things, which is what diplomats like to do. And part of it is also because originally people thought that the ultimate objective of the convention was innocent. Here we are looking at the text of Article 2 of UNFCCC, which says that the ultimate objective of this convention is to achieve stabilization of greenhouse gas concentrations in the atmosphere at a level that will prevent dangerous anthropogenic interference with the climate system. Such a level would be achieved, should be achieved, within a time frame sufficient to allow ecosystems to adapt naturally, to ensure that food production is not threatened, and to enable economic development to proceed in a sustainable manner. It's hard to object to this. Avoiding danger is typically seen as a good thing, and that is something that a lot of people would be enthusiastic about. But it actually doesn't specify a whole lot else, because danger is, of course, a word that is not properly defined. And then in the second sentence, where they try to put some bones on what does this actually mean, they offer just weasel words, right? What is a time frame that allows ecosystems to adapt naturally? What is natural adaptation of ecosystems in the first place? What does it mean that food production is not threatened? And do we mean that food production is not threatened by climate change, or do we mean that food production is not threatened by climate policy? And what do we exactly mean when we say that economic development should proceed in a sustainable manner? It's this sort of, at first sight, appealing language, but if you start prodding meaningless language that allows people to sign up and claim that they've signed up to something good without having signed up to anything much, or so they thought. Because in the first sentence, there is actually a word that at the time people didn't quite realize what they were signing up to, and definitely the drafters of Article 2 did not know this. And that is that the word stabilization actually has far-reaching consequences. Why is it? Let's assume that the concentration of greenhouse gases M is governed by a first-order linear difference equation, so that the stock of greenhouse gases at time t, M sub t, is the stock in the previous period times some depreciation factor, plus however much we added to the atmosphere in that period. Now, what does stabilization mean? Essentially, it means that M doesn't change, that the concentration doesn't change over time, or MT is MT minus 1 for all T, so we might as well drop the subscripts. We have this equation here, and is delta M plus E, which implies that in order to achieve stabilization, doesn't imply any plus. We have M is M is delta M plus E, or M is E over 1 minus delta. So stabilization of concentrations just means that we need to stabilize emissions, and then the concentrations just follow by dividing over the depreciation, 1 minus the depreciation factor. Now this is incorrect. In the very first lecture, I showed this cartoon of the carbon cycle, where the boxes were stocks of carbon on the planet, in the deep ocean, in the surface ocean, in the vegetation in the atmosphere. In black, the numbers at pre-industrial times, red, the changes since. The arrows are fluxes of CO2 between the various reservoirs, and I talked about all these numbers. I did not talk about this arrow at all. CO2 is removed from the atmosphere by a range of processes. Chemical interchange with the ocean, biological interchange with vegetation, but it's also a geological process. And what this arrow suggests, and it says weathering here, that part of the CO2 is removed from the atmosphere by geological processes. Geological processes are fairly slow at the human timescale. Essentially, part of the CO2 is removed from the atmosphere at the rate at which rocks grow. Now, you probably noticed that rocks don't grow very fast. But that is the rate at which some CO2 is removed from the atmosphere. In 1987, Ernst Mayr Reimer and Klaus Hasselmann wrote a paper, published a paper rather, in which they showed that the best mathematical approximation for what is going on in the carbon cycle is not to assume that the carbon cycle is governed by a first-order difference equation, but rather that the best way of looking at the carbon cycle is to assume that there's 5 separate carbon cycles, 5 separate concentrations of CO2 in the atmosphere. No worries. here denoted by a subscript I. And then each of these is governed by the same first order difference equation that I showed before. Of course, then we have to apportion the emissions E into 5 constituents, and the total of those constituents of this fraction should of course add up to 1, otherwise the thumbs up. And then what they found is that about 17% of CO2 is removed from the atmosphere with a characteristic lifetime of 2 years. Another 23% is removed with a characteristic lifetime of 17 years. A bit is moved with a characteristic lifetime of 74 years, 363 years. And a bit, 13%, stays in the atmosphere practically forever. It is removed by geological processes. At a unit time scale, is forever. Right? It's not removed at all. So what does this imply? Well, if you go back to stabilization, what we said was that stabilization M is M. So we need to solve this equation. M is delta M plus E. So M is E over 1 minus delta. But for 30% of emissions, delta is 1. So M is E over 0, which is hard to solve, right? Now there is an alternative solution to this equation here. If we have that M is delta M and delta is 1, then we have M is M plus E. And the solution to that equation is, of course, E is 0. So the only way to stabilize greenhouse gas emissions, greenhouse gas concentrations in the atmosphere, is to drive emissions to 0. So we're not talking about 80% emission reduction, as a lot of politicians seem to think. We're not talking about 90% emission reduction, as a lot of environmentalists are arguing for. No, we signed up in 1992 to 100% emission reduction. As I said, I don't think that the people who designed these languages knew that this is what they got us into. But that is what we promised. Now, there's a big difference between 80% emission reduction and 100% emission reduction. When we were talking about emission reduction, we sort of said that 30% of energy is wasted. It suggests that the first bit of emission reduction is easy, right? Getting changing power generation so that it becomes carbon neutral is relatively easy. We know how to do that. We know that we can do it at a relatively modest cost. Decarbonizing transport is relatively, technically relatively easy as well. It's going to be expensive, but it's doable. But on the same emission reduction, you need to go after the final lease application of fossil fuels. It's going to be what it is. At the moment, there is no alternative to using fossil fuels in aviation. At the moment, there's this trial going on where somebody in a solar powered aircraft is circumnavigating the Earth, right? It's going to take 5 months, and only one person can fly because otherwise it would be too heavy. So aviation is a long way away, right? Probably not the ones furthest away working on advanced biofuels that could replace kerosene. At the moment, it's very hard to imagine space flight without using fossil fuels. Maybe in the very long run. At the moment, it's also very hard to imagine all hospitals switching after diesel generators as backups. Right? So 100% emission reduction is probably order of magnitude more difficult than 90% emission reduction. But that is what you signed up for. Is that justified? I'm going to switch gears here and talk about optimal climate policy. Last term I talked about cost-benefit analysis, and what we found is that if you just assume that there is a static optimum at the first order condition of optimality, or if you just assume a static model, then first order conditions for optimality are that the marginal cost should equal marginal benefits. Uncontrolled emissions, then the further it goes down emissions, the higher the cost becomes. The margin here assumed linear, just for convenience sake. There's no problem, there's no impacts, but the greater the emissions, the larger the costs of climate change and the margin, and then the social optimum is either where the green line meets the brown line, or where the red line, which is just the sum of the two. This one minus this one, of course. The red line is 0. That's where the social optimum lies. That is for a static problem. In calculus terms, essentially what we want to do is maximize welfare by choosing emissions E. Welfare is defined as the benefits of emission reduction minus the cost of emission reduction. It's an unconstrained maximization problem. So we simply set the first partial derivative of the objection function to the thing that we're deciding about, E to 0, because we have the E is 0. So we find that the BDE minus the CDE must equal 0, or marginal benefits equal marginal costs. In a situation like climate change, which is of course not a static problem, the typical assumption that we make is that the costs are a flow. So the cost we incur of emission reduction at any point in time depend only on the emission reduction at that point in time. This is a bit of simplification, doesn't actually change the insight at all for the moment. Whereas the benefits are a stock. That is, the impacts of climate change depend on the sum total of climate change, which depends on current temperature, but the current temperature, because of the momentum in the ocean, is a function of past temperatures, and the current temperature is of course driven by the concentration of CO2, which is a function of past emissions of CO2. So that is clearly a stock problem. So what we do in a situation like this is that we equate the marginal costs of emission reduction not to the marginal benefits, but rather to the net present value of a stream of marginal benefits discounted to today. So one way of conceptualizing or formalizing this is as follows. We still want to maximize some welfare function, which depends on our choices of emissions from today, next year, the year after that, all the way to the future. Then our welfare function W is still benefits minus costs, but the benefits are different, right? The costs we assume to be instantaneous, so that only depends on our emission reduction at time t. That's our cost at time t. But the benefits at time t depend on emission reduction in time t, emission reduction in the year before, emission reduction in the year before that, all the way back to today. Right? Actually, it also depends on whatever we did in the past, but that is immutable, so that's irrelevant for our decisions. We're not making decisions about what emissions would be in the past. Right? Quite true. Because we are constantly redefining how we measure and monitor and define emissions. But let's just assume that the rules are fixed and emissions are emissions, and they will just depend on whatever is going on from here on. So it's still an unconstrained problem. So if we want to maximize this, we should simply set the WDE equal to 0. But now we have a dynamic problem, so we should do that for every t. That's what's going on here. The WDE, right, is essentially dB dE minus dCdE. Now this is unchanged, right? Or rather, this comes with 1 over 1 plus r to the power t, right? So that pops up here. The margin, the benefits now depend on everything that happens in the periods before t. So that becomes a sum. So essentially, we have the VDE just as we had before, but what we now have, if we make decisions about our emissions at time t, that affects our benefits at time t itself. We start from S is 0, the year after that, the year after that, and so on and so forth. Right? So we run this from t from S is 0, so time t, S is 1, time t plus 1, S is 2, time t plus 2. And of course, we should discount that whole thing to t. So you may think, why does this not have an S plus t and this 1 over 1 plus rho to the power t? And of course, those two things cancel against one another. So that is the mathematical structure of this particular problem. He said that the instantaneous marginal cost of emission reduction equal the marginal benefits, or rather a stream of marginal benefits from the point where we make our decision all the way into the future. And that is, of course, then discounted to bring it back to today. Conceptually, this is still the same, right? We equate marginal costs to marginal benefits. It's just that the marginal benefits are now a stream of benefits rather than instantaneous benefits. We actually looked at some of these numbers before, and I showed this in tabular format. In the second week, in the third lecture, I showed the carbon tax needed to achieve a particular concentration target. And the carbon tax needed was the carbon tax that we would apply in 2015, this year, to all emissions from all sectors in all countries, all greenhouse gas emissions. What we see here is not the table with the various models, but rather the median across the studies, and the 76% confidence interval and the 95% confidence interval. This axis is logarithmic, so the function looks linear, but it is in fact exponential. Right? So if we want to achieve, say, 650 parts per million, we should apply a carbon tax that must be around 20. And if we want to go for 550 ppm, we should apply a carbon tax of around $100 per ton of carbon. If we want to go to 450, we should apply a carbon tax of around $800 per ton of carbon. The current price of CO2 permits in the EU is about $5 per ton of CO2, which is about 20 euros. No, it's about $5 per ton, euros per ton of CO2, which is about $20 per ton of carbon. Converting in my head, dollar and euro are about parity, right? So that's here. So if the whole world were to apply the same stringency as European climate policy, not in rhetoric, but as it is, then we're heading for around 650 parts per million. To put this in context, the European Union has adopted as its target that we should control climate change so that the global mean surface air temperature does not exceed 2 degrees above pre-industrial. To have a 50-50 chance of achieving that, we should head for 450 parts per million rather than for 650 where we're heading. So this is where climate policy in Europe is. This is where climate policy, where the climate rhetoric in Europe is, right? And there's a gap between them. Well, essentially, if the rhetoric were to match the reality, we would need to, or reality were to match rhetoric, we would need to multiply the carbon price by a factor 40. And this is, of course, for global emissions, right? So it's not just that we should multiply the price of carbon in Europe by a factor 40, but we should also convince the rest of the world to adopt the same policy, right? So this is essentially the supply curve of emission reduction. This is the signal we give. This is the response that we get. I also talked about what is our willingness to pay to reduce greenhouse gas emissions. What is the damage done by emitting an additional ton of carbon dioxide? That is shown here for modest discount rate, 5% per year, 3% pure rate of time preference. I'll get back to that in the afternoon, what that means. And here for the social cost of carbon good tax, what you see is sort of that our best guess of the social cost of carbon of the good tax that we should apply is around $25 per ton of C. So you can guess where this is going, right? This is how much we should be paying for carbon. This is, if we pay this amount, this is where we end up. The story is not complete, right? Because this is the carbon tax we should be paying in the year 2015. We also want to project this into the future. Here I'm just following Nordhaus's Dice model, where he sort of starts at the same point as, well, a bit higher at 37, 40 or so, and then just let the carbon tax slope up over time with an Italian discount rate. But yeah, it never gets to the 800 I talked about before, right? It gets to about 200 at the end of the century. So if you put all this information together, what do we expect to get? Well, a picture that looks something like this. So in black, this is still results from Nordhaus's Dice model. In black, we're looking at the assumptions about what the concentration of CO2 in the atmosphere would be in the absence of climate policy. And in green, we're looking at the results of welfare optimization. And what you see is what you would expect if you follow the numbers that I just gave you, right? So climate change is an externality, a negative externality, so we should apply a carbon tax of this order of magnitude. If we apply a carbon tax, emissions come down and therefore concentrations come down. But if this is our supply curve of the cost of emission reduction, this is our representation of the supply of emission reduction, then we don't stabilize concentrations at all, right? We opt for emission reduction. Yes, we have a negative externality, but nowhere near stabilization, right? Nowhere near the 450 targets that the European Union is so very keen on, right? In fact, we crossed that in 2030 and never looked back. Now, how can this be, right? Where does this structural difference between welfare maximization and international law comes from? Essentially, Nordhaus asked the question, or anybody who runs sort of a very fast program of emission control asked the question, if the world were ruled by a benevolent dictator, what would she do? That is essentially the question. So we define global welfare and we maximize it. And we assume that there is a global social planner who can enforce whatever comes out. So that is the question that Nordhaus asked. It sort of provides a yardstick for all other climate policy. And the answer that Nordhaus gives is essentially the question is what would Gabriel do? And the answer is not very much. Just like the real one, right? And essentially what Nordhaus found is that we start with a little bit of emission reduction. We start with a gradual deviation from the no control path. We deviate more and more and more and more, but never enough to stabilize concentrations. Now, when Nordhaus first wrote this out in 1982, and then again in 1991, and again in 1994, a lot of people got very upset, particularly about the latter part of the conclusion, but also about the first part. Everybody agrees on the middle part. And ever since, a large number of people have been trying to overturn this basic result. Now, what came out of all that? So this is Nordhaus' conclusion. Let's put it back to 1991. What did the later literature find? Well, Nordhaus' conclusion comes in three parts. We start slow, we accelerate, but we don't stabilize. The first part, starting slow, you can do whatever you want with your model. You can stand on your head, you can change all the parameters. You're not going to change the conclusion that we should start slow. We talked about it in the cost of emission reduction. Because the capital stock that generates CO2 emissions, so the power plants that bring our electricity, our transport systems, so on and so forth, because the capital in these sectors is so long-lived. Any rapid acceleration of a carbon tax or any high carbon tax that is applied initially is not going to reduce emissions by a whole lot. because the short-term price elasticity is low. But a high carbon tax is going to do real economic damage. And essentially, the intuition there is that you're punishing people for decisions they made before the carbon tax could be conceived, right? So however you conceptualize or parameterize the problem, you're always going to find that because of the inertia in the economic system, you just want to start gently, otherwise you're just punishing people for past decisions without reducing emissions. The second part of the Nordhaus's conclusion is remarkably sensitive to assumptions. So Nordhaus says it starts slow and accelerates, but the rate at which you want to accelerate is actually very, very sensitive to assumptions. Different discount rates, different assumptions about growth rate in the economy, different assumptions about changes in relative prices of renewables and fossil fuels, changes assumptions about price elasticities or substitution elasticities. They will all give you different rates of acceleration in your carbon tax over time. The third part of Nordhaus's conclusion is robust. However you can phrase a cost-benefit analysis, you're always going to end up, almost however you can phrase your cost-benefit analysis, you're always going to end up with an interior solution, with emissions that are greater than zero. Why is this? It essentially goes back to the static picture of cost-benefit analysis. And what we do in cost-benefit analysis is we're balancing the marginal costs of climate change against the marginal cost of emission reduction. And the balancing act will almost always get you what is technically known as an interior solution. So there's two corner solutions. One is uncontrolled emissions, that is this corner here. The other is zero emissions, that is this corner here. Now, why don't we go for the corner of uncontrolled emissions? Because there's a negative externality. The justification to push emissions from here to below, the justification that you need for that is just that climate change does some damage at the margin. It doesn't matter how large the damage is. It doesn't really matter where the green curve is, but as long as it's above zero, you're always going to justify a little bit of emission reduction. And the way it's shown here is that reducing emissions by a little bit is going to cost very little, but it's actually going to avoid a lot of impacts. If we assume that climate change without emission control is 6 degrees, and then with emission control we push that from 6 degrees to 5 degrees, we actually avoid a lot of impacts. So that is justified. Now, if we push climate change from 5 degrees to 4 degrees, we probably still can avoid a lot of damage, but not nearly as much as the damage avoided from pushing it from 6 degrees to 5 degrees. But we need to push emissions further, so that is going to bring additional costs. Now, then we're pushing climate change from 4 degrees to 3 degrees. Lower benefits from 3 degrees to 2 degrees. Benefits are becoming doubtful from 2 degrees to 1 degree. It's actually unclear whether there's benefits still from doing so. From 2 degrees to 1 degree, from 1 degree to 0.1 degree. To justify zero emissions, we don't need to say that 0.1 degrees of warming is better than 1 degree of warming. And we don't need to say that 0.01 degree of warming is better than 0.1 degree of warming. No, we need to push emissions down to zero. So we need to argue that no climate change at all is perceptibly better than a global warming of 0.001 degree per century. It's immeasurable, right? Just these marginal costs go to zero, right? Or come very, very close to zero. Whereas, of course, cutting emissions not by 80% but by 90% is going to increase costs. Not by 90% but by 99%, not by 99% but by 99.9%. Keep going up, right? So yes, we avoid this corner. We can just, what did I do now? We can argue that emissions should be reduced, but with a very simple, straightforward cost-benefit analysis. Arguing that emissions should be brought down to zero is actually extremely hard to justify. So that is why Nordhaus found the blue part of his conclusion. We're not going to stabilize emissions if we want to maximize welfare. And that is why this part of the conclusion is extremely robust. It's also extremely popular. And many right-young critics have started their career trying to overturn Nordhaus and failed. There's one exception to this, and that is if you believe so-called backstop technologies. Backstop technologies are very strange things. So the thought experiment is as follows: we impose a carbon tax, right? Because we impose a carbon tax, the price of fossil fuels relative to the price of renewables goes up. Fossil fuels become more expensive, and that means we switch to alternative carbon neutral sources of energy. Cost of energy also goes up, so we also use a little bit less energy, right? Now, a backstop technology is a technology that satisfies two properties. One, if the price if the carbon tax is high enough, then the technology will take over energy supply completely, right? If the price of carbon is high enough, then we will phase out fossil fuels. That is one crucial assumption, that there is such a technology out there. And if you look at individual sectors, most individual sectors, then there is indeed such an alternative available now or on the horizon, with perhaps the exception of space flight, and the cost would be simply to stop going into outer space, right? Bit of a problem for a communication network, right? Because of satellites will come down eventually. So that is the assumption, right? There is such an alternative source of energy out there, and that's an assumption that is reasonable. However, at that point, of course, the climate problem disappears. Right? We phased out carbon dioxide. That means that we stabilize the concentrations. The concentrations will be stabilized. At some point in the future, that means that climate is going to stabilize, or at least the anthropogenic part of climate is going to stabilize. And at that point, you lost your justification to impose a carbon tax. The second crucial assumption, crucial property of backstop technology is that when you abandon your carbon tax, when you reduce your carbon tax to zero, fossil fuels are not going to come back into play. Which is a very strange assumption to make, because we know how to use fossil fuels, we know to mine them. And the alternative technology came in by virtue of the carbon tax, which suggests that this is a technology that is more expensive than fossil fuels. And the fossil fuels are still out there, right? So the assumption that you need to make is that first, because of climate policy, you're going to introduce a new source of energy, and then by some magic, that energy is going to fall so much in price that fossil fuels will never ever compete again. And it's particularly the latter assumption that I find totally incredible. But there are some people who swear that this is how the world works. If you're prepared to make this assumption, then you're going to stabilize concentrations of CO2 at some point. If you're not prepared to make that assumption, then you will not. So, that was the first part of this story. Next week, I'm going to talk about what happens if we have many countries, and if you have countries acting in their own self-interest, then of course the implication is that if you only care about the impacts of climate change that fall on your own jurisdiction, then you care less about climate change, right? Because your own jurisdiction is a fraction of the world, and that implies that optimal emission reduction goes down. So that is next week's topic. This afternoon, I'm going to return to this question and start playing around with some of the parameters that guide the results and see how robust some of these things are, and definitely the bits to different assumptions about discount rates, risk aversion, inequity aversion. Okay, I'll see you guys then.